I'm super happy that we have in 3X MX3D because we all were jealous about your first videos. These two white robots crawling on top of this structure being built on a canal in Amsterdam. And now seeing all the changes and how they say technically developed, but also aesthetically developed. We had a good talk yesterday about that. That's really, really impressive. We have here Gijs, he leads MX3D. The interesting thing which I learned yesterday, he's actually a lawyer.
I am.
Oh, that's an interesting one. Worked long for an artist in an artist office, running the company for this artist, and out of this artist, this MX3D developed. And they're currently doing a lot of research. They're doing a lot of, say, projects for others who need something special. And they're intensively working on this bridge to be installed. And now it's yours.
Thank you.
Applaus.
Yeah, thanks. Great to be here with all these nice large-scale 3D printing projects. Hopefully a nice intermezzo with metals now. So, indeed, our bridge has completely changed the look, and that has many, many reasons. Some of I will talk about during this lecture. But this was the presentation during Dutch Design Week in October 2018. So the bridge is finished, and unfortunately we're waiting for the city to finish the work on the canal walls before we can place it. But we have heard that February is a very likely date. So we're rounding up the permit, and hopefully they can close up the works, so this bridge will be actually in use. So we started out with the vision when we worked with robots that we thought robots will come in and start being builders on the work site, doing everything fully automated, and yeah, we could step back and look at all these beautiful new buildings with the new aesthetics being built without our intervention. But yeah, that takes a bit of work before you get there, as we've seen before. So there's a lot of learning to be done after this first concept arose, and yeah, we fortunately had a bit of background with that. So as already mentioned, we are coming from a design agency, Joris Laarman Lab, and he was investigating the way these new digital tools, whether physical making machines or digital tools that you use on the computer to design, are going to change the way our world looks. And of course he focuses on trying to make this good design instead of lower cost or other efficiency ideas. He wanted to experiment what kind of crazy changes this could mean. And this is one of his first projects where he, together with Opel and a professor in Germany, developed an algorithm that imitates the way bones grow. And they did iterations in 2006. It still took 2 weeks for an iteration to come out. But eventually they found a really nice, naturally designed way of building a chair. But of course, a chair like that you can not create with classic manufacturing tools. So this was the first time that we got involved with 3D printing. So a bit similar as concrete printing, but a sand mold printer with a binder. That was the closest thing we could find to create this metal structure. It's an aluminium chair. So we could create all these kind of nice cooling channels that allowed the chair to cool down at one rate, so it wouldn't start pulling apart during the tension there. And after that, of course, we did a lot of sanding and polishing, which is always a nice part of the job. We did a lot of projects. Many of the projects were about 3D printing or algorithmic design. And one of the projects I want to show is the metal printed gradient chair, also an aluminum chair, so it's basically an evolution from the bone chair. And it was the first time that there was a metal printer available to do these kind of projects. So we completely optimized the chair. It's very light in places where it doesn't need, so you can actually see through the seat. But it has a fully massive legs where it has all the forces to deal with. But we realized with this project that SLM, selective laser melting, is not going to be the technology used for large-scale structures. So we started thinking, so how can we change this? How can we find a way to print larger at lower cost, but also with higher speed? So first we did a project with a robot and resin in 2012, 2013, and we still had that robot, and then one of us came to the idea, why don't we hook a welding machine to it? And that's the technology that we're now developing. So we have a standard robot, standard welding machine, and we try to make that a 3D printer with the software we add. Now we have added a small component that takes in all the data from the sensors, but still a relatively simple machine compared to the high-cost SLM machines that were used to make the chair. And at first it was just about experimenting. So we wanted to see, can we imitate the way we worked with the resin, so draw lines in mid-air with metal. And to our surprise and to the surprise of many of the welding experts that were helping us, it actually did work. As long as you took time and didn't think about material properties, but just experiment to see how you could make the next dot on the next dot, and how you could make the toolpath to make all that work. So after these first experimentations, we realized that, okay, we really need a little bit more software to make this happen. So over the last 4 or 5 years, one of the things we've worked on most is creating the software package. This allows you to input an STL file, and then every step is dealt with within one environment. Unfortunately, other toolpath planners were not dealing with the specific problems that wire arc additive manufacturing had to deal with, and I'm sure with concrete you have the same things. You have a couple of these specific things you have to do, and they are just not dealt with the standard tools that are available. So it's just one workflow, and most importantly, it takes in process control so that you can, once you understand what's happening, you can feed that back into the... Is that me? So once you have all that data, you can start feeding it back into the slicer, and you can start improving the process based on the data. So data-centric engineering in a way. So the first object we made with this was the bicycle. It's an aluminum bicycle launched in September, I guess. And here we really try to show our audience for the first time is like, okay, we now have this tool. So if you want to start printing for yourself, you can knock on our door. And that's also what we're doing here at Formnext. So we get a lot of interest in that. But yeah, the same themes are dealt with in every object we're making. So of course, topological design is very important for us, because every kilo of metal we deposit, it takes an hour or half an hour. So we really need to save all the material we can. So it's not even an environmental idea, or it's just a pure time saving, and making a bike like this now takes around 20 hours. So we start to get to a point where you can make metal objects like this, specific editions, within a reasonable time frame. So we experimented a lot. It was great to not be maybe engineers or architects and have this larger vision already to deal with, but we just started playing around, discussing with artists what they wanted to make, and then telling them what our software could already do. And then we just started printing. And doing it helped us learning what this process really meant, what it could do and what it couldn't do. So we slowly developed a good idea of what metal 3D printing this way could mean. So we have several different strategies. So one is printing lines, and we could make a bar for Herzog de Meuron Museum in Miami. So it's now standing there. If you're ever there, it's a really nice place. The museum is a cool building with a nice bar and a view on the swamps there. So it's a nice place for a drink. But our biggest project to date is the 3D printed bridge project. And we started with the same vision. So we said, once you have these robots, why not just send them out in nature and let them build whatever structure you need. Maybe you do some data analysis on the red light district, and you see, oh, we really need a bridge here and there to increase the flow of people. So you can just let them go, and they'll build whatever. Fortunately, probably the city quickly told us that we were not allowed to print such an innovative bridge there because there's millions of visitors there, and they more quickly saw the dangers of a project there than us. We also developed a lot of the printing required for the robots to crawl over the bridge, to print horizontally, but it didn't really come together yet for this project. We think we could do it now, but the question is whether it would be an effective building of a bridge. So we did this not alone. I mean, we definitely didn't have the skills in-house. We were makers, enthusiasts, but we weren't roboticists or software specialists. We definitely didn't have the engineering power. So we gathered a whole group of people around us, and instead of signing thick contracts with IP clauses in there, we just said, what comes on the table is for everybody to use. You can do whatever you want. The only rule is that you contribute what you can from your specific specialism. That worked really well. Many of these partners are still with us and included in new projects we do. This is the bridge we're replacing. Quite a simple bridge to replace aesthetically, but we are definitely confronted with a bridge that is very well used. So you have 15 million visitors, and it's not unlikely that the maximum load capacity of this bridge is actually being tested quite a lot of times. So that's also what we did in Twente just this month with Imperial College and Twente University. We put 20 tons on it. It maintained perfectly, so that's, I believe, 1.3 times the maximum load capacity that we needed to go for. And then we also, to test our assumption, is to see if that in real life would be sufficient, we put as many people on as we could, and that was around 90 people, 6-7 tons, I think. So yeah, we feel that we concluded a nice conclusive test about the stability of the bridge. So last year we also spent some time on the fracture mechanics module. That was one of the parts that was more complex to show to the city that also there is not a problem. And yeah, putting a sensor system in place to understand how the bridge is behaving while it's being used. So, as mentioned already, we went through an enormous design process. Joris Laarman and Arab had almost 2 years going from the original concept where you use the tree-like, bone-like structure to hold up the bridge from the current design, to the current design. So one of the reasons why this bridge eventually got kicked out was the fact that if you run into one of these members with a boat, you can have a catastrophic failure. And because we didn't want to over-dimension it that much more, this just didn't seem like a feasible solution. Also, we couldn't put forces on the canal walls. One of them at least is very old, and there's no drawings. And they just said there's no way you can put any forces on that side of the canal wall. So we had to put a bridge on the top. Being 2 years in the project, quite desperate, money running out really fast. We said, okay, we got Arab on board as a big partner, and they started designing together with yours from a much simpler concept based on all the material research we had done by then. So we were 2 years in the project, so we had done a lot of buckling and tensile tests to come up with new models that showed that this design approach would be a very high chance of succeeding. In the meantime, even though not all the scientists were agreeing with our approach, we said we're just going to start. After 2.5 years, we couldn't wait anymore. We just wanted to show us and the world that we were able to print the bridge as we said. So we just started printing. And we also put the robot on top, not yet with a mobile support, but we printed horizontal, which worked, but it was almost 0.5 kilo per hour, and we rather had around 2 kilos per hour as we had to deposit 6,000 kilos. So yeah, the gain from increasing the speed slightly was clear. So we chose, it is the object to print a 3D bridge. So let's print it in very big parts and then assemble it together. And the irony is that the assembly lines, the seams that are manually welded by a construction company that does a lot of stainless steel structures are the worst welds that are in this structure. And if it's going to break anywhere, which it's not going to, but then it would be these welds that are placed. So Arab has shown that together with Imperial that these spots always come apart when you pull. So the next addition to the bridge is to put a big sensor grid on it with around 100 sensors. And the idea behind that is to, one, have a good idea of how the health of this bridge is over time. But also to understand how such a monolithic structure, a steel structure with a quite special shape, is behaving when it's becoming hot, loaded, when cold, etc. And also maybe when there is some changes in the structure, we can see that. But another use case of all this data is that we can put it in a digital twin. And that digital twin is going to help us when we will build the next bridge. So we can constantly update the material properties that we use for the design, but also understand how the bridge we made was behaving and see where we put too much material and where we could reduce. And we can all imitate new designs in this model to see whether they actually make sense. So we hope that in a couple of iterations with a bridge like this, you can actually come up with a computer-aided way of designing bridges. And even though I don't believe that this means that engineers and architects are out of a job, but they definitely will have a shift in tasks in placing and designing a bridge like this. So what we think is that you will have algorithms like this where you just say, okay, you have to span 8 meters. These are the load case. You have to depend on the space where you go under is this. And then just let me know what kind of options I have. Architects, city can choose which one they like the best and go for that. And then the design and the engineering can all take place in this one model. Of course, once you start printing, you can log everything you do so you know exactly how it's printed. When you then sensor the bridge and there is something that you don't really understand, you can go back in the logs and see how it is that the digital twin is different than the real situation, and you can start researching that specific thing. So maybe some of you have already seen this, but we made, for October, we made a small video to summarize everything we've done so far. Of course, in February, March, we hope to come out with a new one where it's actually on location. But this was the whole part of the 4 years of development where a lot of testing was involved, a lot of sensor trying, and a lot of fun as well. So we hope this project can be repeated once more, and then we think we can do it 3 times as fast and for hopefully 4 times less budget as well. So by then we also get into a zone where it's still an expensive bridge, but it's not that crazy anymore. And hopefully that evolution will go on. So in 10 bridges you will have a bridge that is just as expensive or even less than regular bridges. Of course the design has to be optimized. I mean, it's now a very big design with lots of metal in it, and you know, for a 3D printing concept, you probably want to take away all the metal that you can, even though the handrails have a large function in the structural soundness of this bridge. We definitely think we can make the next bridge with a lot less printing time. So what's next? MX3D has been working on the background, as I said, on the software we're making. We're also involved in European projects where partners help us to close the loop. So on the design side, but also on the certification side, we're definitely necessarily our specialty, but with these 24 partners, we have expertise of all these different sides. And that's also still how we think about this development. I mean, when we started, there was about 10 publications every year on WAM. Now we have around 500. But this helps us. I mean, we read these publications as well. So we really think that that new technology like this you cannot do by yourself. It's with concrete as well. I've seen the amazing shoot up the last couple of years, and that's all because everybody is publishing what they're doing, giving each other ideas, and moving quickly beyond to a next phase. And I thought the roof with the spray concrete was a very nice, elegant concept, and it also economically I could imagine that could work well. So what have been here at Formnext? So we think that printing large bridges, perhaps 3D metal printing is a relatively slow process, so that will take some time before that becomes economic. But definitely for cubic meter size objects, a lot bigger than SLM, but also not so big that it's 5 or 6 tons of metal. So we took a robot arm. We scanned it in, we optimized it with the help of Altair, and then we reprinted it 50% lighter than the original part. To be fair, we didn't take in all the load cases, the maximum load case, but we just took in the load case that we needed. So the idea is really that you can now make a custom arm that ABB doesn't deliver because there is not enough interest in. But for a specific case, this could be a very good solution. Hopefully we'll send you the movie where we have this whole operation actually working. So we have the whole robot. We're going to install it. Hopefully the software and the safety mechanisms in the robot are not going to be a problem. But then we can show that this is a functional part. More relevant to construction is the connectors we've been working on. So from the very beginning, for me, it was very clear that you couldn't print whole houses or whole buildings, but that in a parametrically designed structure, it does make sense to see if you can print the places where everything comes together. So you use standard beams, but the central point, that is something that takes quite a lot of manual work. Labor in this kind of specialty is not so available anymore, so it's quite likely that we can achieve a level of speed and quality that allows the architects or steel structure makers to start implementing these kind of solutions. So what we did here was a project with Takanaka, is a Japanese construction company, and they wanted to design a connector. They just said we have 4 wooden beams, they come together like this, and we need to fill that design space in a functional way. So we used a similar optimization process. We get some hollow spaces in there to fill it with concrete, just like bigger connectors are done in real life, and we printed it, and now fortunately Takanaka was so happy with the result that they wanted to implement it, and we're now working towards a plan to have it installed in a building with a couple more nodes as soon as possible. Can't yet give a timeline on that because the safety, of course, here is just as big an issue as with the bridge. But this is our next big project. I do have a small video of this node which just came in, so it is still too big for the presentation. So I'll just show that as a closing part of the presentation. Thank you.
Obviously, open for questions. I have one. Why do you use concrete in that steel structure?
Well, it's a good question. I'm not an engineer, but this is a strong demand for the Takanaka. They say they do this to prevent the node from deforming under pressure. But I'm still have to owe you the answer on that.
Okay. Well, you were very honest by saying, this kind of question is something for these engineers.
I think so.
Have to check.
Yeah.
Okay.
I think it's mainly you know, they have done that before in other nodes similar like this, so they want to show that that's possible here as well.
Common technology,
yeah.
they're aware of, and trust, which is something which with the
Japanese
also works like this.
Yeah.
Questions? Any question? Come on, this can't be. This is super prominent. There we go.
I'm curious as to whether the topology optimization you said it takes into account different load cases. Do you know, does it deal with buckling, vibrations and that kind of thing? You had people jumping on the bridge, so I'm wondering if that's accounted for or is that checked afterwards?
Yeah, no. Well, I mean, we rather not check that in real life. So we did all the tests there. So yeah, I mean, there's not everything we can show, but we put not only the buckets of water on there, but we made some dynamic tests as well. And it's yeah, we did all the tests we could imagine that were required to convince the city to believe that this is a safer structure than any of the bridges they have, because of course for them it's also very exciting to put the bridge in the city center where it's so busy. They cannot afford any failure on that. So we did every test imaginable. But maybe after the talk I can tell you who did it and who made the nice papers on that.
And if I may, could you talk about the material properties of the steel and how that differs from kind of normal duplex steel? Is it more brittle, for example?
The material properties change. So once you print it, it's not the same as cold rolled steel or even as welded steel. But what we see is that there is a very constant properties that are for many cases well beyond the benchmark of the welding wire. Sometimes they're a bit lower and in some direction. So you have, like with most 3D printing, there is a direction effect. But there is good ways of designing for that. For instance, making a diagonal print so that you can use the forces in a different way. But even in the print direction, it's a very workable metal that has constant values. But Victoria there next to you can tell you more about that.
This is a good placing. Jörg.
Okay, thank you very much. I'm looking on your projects with a little bit of envy. But talking about our building authorities, I think it's very smart to include the monitoring, because we have a new technology, we don't know everything about the material and about the structure. So I'm wondering what kind of sensors you use and how you make sure that these sensors will stay there for years?
50 years.
Yeah.
Not 50 years, but years.
Yeah, so there's a couple of things to say on that. So we use the regular sensors that you use for a bridge health monitoring system. So well, I mean, I'll show you the list for that after. But the idea there is that it is a very simple and robust system. That's also what TU20 is doing now. So we made for the Dutch Design Week, we made an initial concept. It worked. We had all the software behind it that made it work. And then now we're making it ruggedized. So it's in the red light district. So you need no chance for anyone to be able to touch it. So we're actually going to close it up on the bottom, which is a bit of pity because of the design. But on the other hand, for the sensing, it's important. One other aspect we have agreed with the city is that we measure the bridge. It's not a 50-year project, but a 5-year project. That made it all a bit easier, and of course we hope after 5 years that all the data shows that it can easily stay longer. But we cannot prove now yet that it is a 50-year bridge. But this data hopefully shows that there's no change in behavior over time. So that's going to help us there. But I'll inform you on the sensors we used after.
They're going to have contact anyhow in the next steps. No, I'm not going to. Sorry, Harald. We're running just 3/4 of an hour late, so let me push a bit. Sorry. I'm super happy that you showed this. The interesting thing is the artist is coming to push something. So this is really, not trying to find the typical engineering way of finding money different, then coming with a different attitude. Not only having the structure design as an aspect, that really gives an impact. And that's actually something which we need a lot more in these kind of environment, more projects which are asking what we can do with it.
Yeah, I think we changed the way we approach such an innovation project. We just want to see if we can realize it first, and then we can find a use case for it. And that's
super nice. Thank you for coming.